T and B give a natural frame of reference for this curve. We'll also want to examine some other characteristics that are sort of natural to the curve. The first thing is we have this parameterization that depends on t, so we can get t, n, and b in terms of what time it is, but it might be more natural to specify points on the curve not by what time it is, but by how far we've traveled by a certain time. So we're going to let s be the distance that we've traveled, or by some time t. So s, which is going to be a function of what time it is going to be the arc length parameter. So instead of thinking about where we are by what time it is, we'll think about where we are by how far we've moved along the curve. So we'll investigate this arc length parameter. Okay. We'll also be interested in how does the unit tangent change, because if the unit tangent is changing a lot, then we would think that this is a very curvy curve, right? And if the unit tangent is pretty much constant, then we would think that our curve is fairly straight. But it doesn't make sense to look at dt dt, because dt dt, that depends on the parameterization that we use. We could have a parameterization that goes over the curve very quickly, or one that goes over very slowly. If it goes very quickly, then dt dt will be large, right? Or if it goes over it very slowly, then dt dt will be small. So what we'll do is, instead of looking at how the unit tangent changes with time, we'll look at how the unit tangent changes with distance traveled. So we'll be interested in dt ds. Now this will be a nice measure. This has both a magnitude and a direction. Now the direction, because this points in the same direction as the unit normal, the direction is perpendicular to the curve. But the length of this vector is a measure of how much the curve is bending. So we'll call that kappa. This is a Greek letter K for curvature. So this is kappa for curvature. So that will be one thing that we're interested in. Another thing we'll be interested in, not just the way that t changes with s, but also the way that the normal changes and the binormal changes. Turns out that we'll end up seeing that if the binormal changes, it's going to be in the direction of the normal. So change in b is going to be in the direction of the normal, and it's going to be equal to a number here minus tau. Now, if b changes in the direction of the normal, it's going to be rotating about the curve. And so we call this number here that measures how strongly b is changing. This gives the direction, right? That's a unit vector. This gives us the magnitude. We call this number tau the torsion. So turns out that dB ds will be minus tau times n. So this number tau is the torsion. Tau, of course, is this Greek letter for t. So we'll look at the arc length parameter, right? This measures how far we've gone by a particular amount of time. We'll look at kappa, which is a measure of how rapidly the unit tangent is changing, not necessarily with time, but something that's independent of parameterization with distance traveled, right? So if for a given distance the unit tangent changes a lot, then the length of this vector will be large. We'll have high curvature. But if for a given distance the unit tangent doesn't change much, then kappa will be small. That means we are not curving very much. We have a fairly straight curve. And then we'll look at the rate of change of the binormal, which will tend to be twisting around the curve. So we'll measure that through this number tau, which is torsion.